Now, you see, question 7 starts to get tricky. So that's why I told you to secure your marks in the earlier parts of the paper. But part A should be like quite okay for you. Okay, so given that P dot Q is 0, please take note of the error here, right? So in the question paper, they have made an error, right? This 0, it should not be bolded because the bolded 0 in paper, it means a 0 vector. So it should not a 0 vector because why? Scalar product suggests a scalar. Dot product is a scalar, so it's 0, right? Then what can be used by vectors P and Q? So this is very obvious, the most obvious content you have seen. Right, I already told you the 99.9% guarantee in my vectors masterclass, right? So this means that vectors P and Q are perpendicular to each other. But ladies and gentlemen, I know a lot of you write this and a lot of you are correct. Yes, you are correct, right? But you are only going to get 1 mark out of the two. 1 mark, right? If I say the marker was straight. Why? Because there are two other alternatives you need to consider. What if P was a 0 vector, Q was a 0 vector? Then how? Yeah, so we need to consider these two as well, right? So I'm going to so this one, as you can see in pink, I very nicely go and copy paste every single word for my vectors masterclass, right? I just basically replace the vectors with P and Q, right? But for for this option number 1, this is only true if P and Q are non-zero vectors, right? So you need to go and write this down. If P and Q are non-zero vectors, right? And then options 2 and 3, quite rare, but it's also a bit possible if P and Q are 0 vectors, right? And then but I'm not sure whether this will also let you get too much. So if let's say like you all have time, right? You all have time. If you all don't have time, then just get 1 mark of 2 lah. Just so you can write P and Q are perpendicular to each other lah. But if let's say you all got the time, right? Then try to aim another mark. Like go and prove like using the geometrical definition, because ultimately this result is proved using the geometrical definition of dot product, right? So P dot so let's say P dot Q, right? P dot Q equals to 0. So P dot, so I'm going to say, oh, okay, P dot, so since P dot Q is 0, right? I apply the geometrical definition here, right? And then because the modulus is always, the magnitude is always more than 0, right? You should know that modulus and magnitude is the same, huh? If you don't know, please refer to my equations and inequalities masterclass. Okay? Then you should be talking about this thing is equal to 0, and then you take a cosine inverse, the angle here is 90, and that's the reason why P is perpendicular to Q, right? Usually, I don't, not Cambridge has ever complained that they don't recommend students write this, but I'm not sure whether they will deduct marks. So let's say you got time in exams, better to go and write this full out. It's perpendicular to, okay? Now, part B starts to get more and more difficult. Part B, it says, with respect to the origin on the xy plane, right? There's a fixed point G and there's a variable point R. And then they give you a dot product that is equal to 0, right? So then they ask you to use the locus of R. So ladies and gentlemen, do you know what the word locus means? For those who don't know, I will give it an explanation later. But now, I want you to go and focus on this detail alone. This detail alone is connected to part A. That's the reason why they go and ask you to prove part A, right? What can be used about just P and Q? So again, this is a very similar theory, 99.9% guarantee, right? So this means that R is perpendicular to R minus G. This is a 99.9% guarantee. The only time where this is not guaranteed is when R is a 0 vector, or when R minus G is a zero vector, right? But never mind, later I'll come to that when I discuss about locus. So this remember this fixed guarantee. This is a guarantee, is an if and only if, assuming that they are non-zero vectors, right? So this is hardcore content, I say again. Then I want to ask yourself, okay, that G is a fixed point, right? Which means G cannot R is a variable point. That means R is the one changing. So how is it possible for R to go and satisfy this dot product equation over here, right? Such that R is perpendicular to R minus 3, right? How is that even possible? And that's when now I want to talk about locus, right? I want to talk about locus, right? So as you have heard, as you have heard your lecturers say about this, right? Locus is a set of points that satisfy a common mathematical property. But unbeknownst to them, they have not even explained what is the true meaning of locus to you. So what I'm going to do now is I'm going to do a side track, right? I'm going to do a side track and then I'm going to talk about locus. So I'm going to erase all this, right? I'm going to erase all these things over here. And then now I'm going to talk about locus, right? Okay, so this is a side track on locus. Okay, so locus is a set of points that satisfy a common mathematical property, but do you truly know what that means? If not, please pay attention. Now, when I say a set of points, right, it obviously means that there is more than one point. And sometimes these points, right, can even be infinite number of points. And then now it says satisfy a common mathematical property. So when we are dealing with locus, I was trying to ask yourself, what is the common mathematical property that is satisfied? Right? Because the common mathematical property that is satisfied will be written in the question for you. Okay, so let me give you an example now. Okay, let me give you an example now. Okay, so let's say, I'm going to go and copy paste an image, right? I'm going to go and search and for the image of something, and I'm going to go and copy paste. Okay, so let's say I'm going to search, right? I'm going to search this image here. Okay, so I'm going to copy paste this, right? I'm going to copy paste this, right? Give me a while. My computer is not functioning. I don't know why. Okay, so I successfully copy pasted a star from the image over here, right? Okay, so let's say I'm going to talk about this, okay? Assuming that this string is two-dimensional, right? Find me a point that is 1 meter away from a star, from this star over here. Or let's say, sorry, 1 centimeter, right? Okay, so what will you think you will do? Right. So what I'm going to do is you're going to take a ruler out, right? You're going to take a ruler out, and then after that, oh, okay, you're going to put, let's say, oh, the center of this star, you're going to mark it here, right? Okay, so the center of the star, you're going to mark it here. Mm, then after that, I'm going to like, oh, okay, I'm going to very, very safely claim, wait, am I sharing the correct screen? Okay, good, 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 good. Okay, so 1 centimeter away from the star, we are going to measure, right? So this is the center of the star. Let me see my ruler. Right, so this is center. So this is the center of the star, right? 1 centimeter away should be here, right? Now, where is another possible point that they can lie 1 centimeter away? Some of you can visualize it. You will say, "Oh, shouldn't it be here?" Right? Shouldn't it be here? I mean, yes, that's also possible, right? Okay, let me use a thicker pen. Okay, a thicker pen, then y'all can see. So shouldn't it be here? Shouldn't it be here? Ah, okay, okay. But now, you know that this is just 2 points, right? If let's say, I am going to tilt the ruler, right? Ah, yeah, this stupid one note, I don't even know how to go and tilt. I don't know how to go and tilt my ruler. Okay, so because I cannot tilt my ruler, okay, so because I don't know what's wrong with my ruler, right? So I'm just going to like manually go and mark out some points, right? So some of you might ask me, oh, okay, you're going to use a ruler and measure, right? And then I'm going to say, oh, okay, couldn't there be like 1 point here as well, right? There could also be 1 point here, right? Then, okay, this one's a bit out of shape, so there could also be 1 point here, right? And then, some of you might also ask me, oh, couldn't it be like, oh, vertically above, like vertically below, right? Vertically below, could that be also like vertical? on the left, on the right, on the star, right? All these are a set of points that is 1 cm away from the star. So what is the mathematical property that is satisfied here? The mathematical property that is satisfied that this common, right? You see the word, I say the word common. Why common? Because it occurs for all of these points that I mark out over here, right? So what is so common about them? The common thing is that they satisfy the fact that it is 1 centimeter away from the star. And these are just 8 points I mark up. If you were to go and like, let's say, go and take a ruler, go and draw like, 1 centimeter here, 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 1 centimeter here. You notice you have so many infinite points, right? And once you have marked out all these points and then you join them, right? You join them up, you notice that all these points, right, is going to end up in a circle, right? In the circle. So basic shapes, right? So as you can see, this is the circle that is connecting both these points together, right? So what is the locus of the point that is 1 centimeter away from this center star? It is actually a circle, right? It's actually a circle. There's one example. Now, now this is just primary school math, okay? Like what is 1 centimeter away from the star? Okay, now let's go and talk about secondary school math. Okay, secondary school math. Okay, so let's say I'm going to use the same star. Okay, I'm going to use the same star, right? Why is my computer not functioning? So annoying. Okay, so I'm going to shift this star to the left, right? Okay. Now I'm going to say that I want to find a point that is equidistant from both stars. So one obvious point I'm going to talk about is again the midpoint, right? So like midpoint, right? This is the most obvious point. This is the most obvious point, right? Because the distance from here to here is the same as the distance between here to here. But is that the only point? No. What if let's say I took a point another here, right? Another point here, and then after that I go and try to go and draw the distance, right? So see this distance and this distance is the same. They sort of form an isosceles triangle. But what if let's say, oh, I try to take another point here, right? I'm going to try and take another point here. Right, you notice that if I were to go and take my highlighter to go and draw the distance, right? This distance and this distance is going to be the same. Yet another isosceles triangle form. And then you can try doing it yourself, ladies and gentlemen. I'm just going to plot infinite points, this distance the same, right? Then I'm going to plot points here, this distance the same, right? And then all these can just go on and on, right? Then this distance the same, right? So what we're going to do is you're going to go and join all these points now with a best fitted line. And ladies and gentlemen, remember your secondary school math. I say again, remember secondary school math. As you can see, right? Now I say the word equidistance from both stars. So what kind of a line is this? Okay, if your answer is the perpendicular bisector, bingo, you are absolutely right. Right? Why? Because you see, this is like the straight line joining the two stars, right? And then you have to go and like pick these points and then draw down the straight line, right? You notice that they are actually perpendicular, right? They are actually perpendicular to this line. And not only that, right? Not only that, because of the word perpendicular, because of the word perpendicular, right? Or what I call that, they are equidistant, right? They are equidistant. So that they actually results them in using this word called bisect. Because what does the word bisect mean? Bisect means cutting them to two equal halves, right? Cutting them to two equal halves, right? And then moreover, this and this is going to form an isosceles triangle. And that's the reason why when you go and join all these points up together, it's called a perpendicular bisector. Please remember your secondary school maths. I say again, bisect means go and cut these two distances into half. That is the reason why I use the word equidistance. It is equidistant from these two stars. So what is the locus of the points that are equidistant from these two stars? The locus is the perpendicular bisector. So in this case, The locus is a line, right? Sorry, my line not good. So I'm going to shape it here, right? Uh, and after that, this is the straight line joining the two stars. This is equidistant. This equidistance. Then this one should be the perpendicular bisector. So the blue color line is the locus, right? Now, let's give you one more example. Okay, let's give you one more example. Okay, so now let's say I know what's wrong with the Okay, so let's say I got two lines now, right? I got two lines now, right? I got this A, this is B, then this is the origin. Okay, now ladies and gentlemen, go and find me a point that is equidistant from O and OB. Some of you might write noise visualization skills and say here. Some of you can also say here. Some of you can also say this point, right? Or some of you can even go very close to the origin and say it's here. This and this equidistance. So what angle line is this? The line that joins them together, if you recall a secondary school math, is called the angle bisector. So what is the locus of the point that is equidistant from OA and OB? It is the angle bisector. Why is that equidistant? Because it bisects again. I say again, bisect means cut them into two equal halves. So this angle here and this angle here is the same by virtue of the meaning of angle bisector. Right? Okay, so I hope that this is like sufficient for you to go and explain what locus is, right? So locus can also be of the point that is equidistant from O and AB, and OB is the angular bisector of angle AOB, right? Okay, so this means that locus can exist in the line, can be exist in the curve, or even in the circle, right? Any shape, because there are infinite number of points, right? So now let's go back to this question. Okay, let's go back to this question. Okay, so so let me go and go back. So now let me go back to this question. Okay, so how is it possible for R to go and satisfy this, right? Given that G is a fixed point, okay? So G is fixed, means again it cannot move. Now, R perpendicular to R minus G. If you do not know, ladies and gentlemen, please draw a diagram, right? I said again in vectors, you're going to hear me saying this until you're so damn tired of me. Please go and draw the diagram out, right? So the moment I draw the diagram out, I've concluded these two are perpendicular to each other. No negotiation, right? So this is obviously one possible scenario. This is obviously one possible scenario. But what if, let's say, you can see here, I go and this ORG, right? Sorry, ORG, they actually form a right angle triangle. Because O and G are fixed points, they cannot move, right? But what if, let's say, I have to draw another right angle triangle here? There is also another possible point of R, right? So you see, from here, I read from two possible points of R. Right? Makes sense, right? Now, if let's say I'm going to repeat the same step, right? I have to draw infinite number of right angle triangles. I'm going to see that, oh, okay, there's R here, there's R here, there's R here, there's R here, there's R here. Okay, the blue vector is R minus G. Okay, the blue vector is R minus G. Okay, so because this is OG, so minus G is here, so R minus G is going to go this way. So the blue vector is indeed R minus G. The pink vector is the R, right? It's position vector OR, right? So we're going to draw infinite number of right angle triangles. There's so many possible points of R, and once you have drawn this up, you'll notice that because this OG here is a common straight line, right, that satisfies all right angle triangles, right? It's the common hypotenuse of all right angle triangles. So that is when you recall your geometrical properties of right angle in the semicircle. So remember, the right angle is transcribed by the circumference of the semicircle, and this is subtended by the diameter, right? So OG, especially since OG is a fixed line. So the moment I try to connect all these infinite number of possible points with infinite number of right angle triangles, right? If I'm going to say that R is a circle. And then after that, it's parallel to the XY plane with OG as its diameter. Why did I say it's parallel to the XY plane? Because the question restricted it to be two-dimensional. The reason why they have said this is because the question has restricted it to be two-dimensional. Like the two-dimensional because XY plane. XY plane is two-dimensional, right? Okay, then some of you might, like just now, some of you might ask me, this one super rare. If you actually go and then you're going to ask me, right, how is it possible to satisfy R dot R minus G is zero? If I, let's say R is a zero vector, can. R can be a zero vector. See? Variable point R. Because you have to scroll here. What if let's say R was on the origin? Right? The circle also passes through the origin, right? So OR is a zero vector. R dot R minus G is zero. Right? Okay, so this is confirmed the answer is the pass through OG, and not only that, must specify that OG is the diameter because of this geometrical property. So the key takeaway is they need to relate it back to secondary school geometry. But if the question did not say on the XY plane, right, then it does not restrict it to a two-dimensional plane, right? So it's going to be a three-dimensional real-world application. So then you're going to say that it is a sphere, right? It's going to be a sphere because circle, two-dimensional, sphere, three-dimensional. But the fact that OD is the diameter, the OG is the diameter, still does not change. Okay, so these are the learning points for you to go and read, right? So the locus always means that it's a set of points that satisfies a common mathematical property. So the next time you're dealing with locus, always ask yourself, what is this common mathematical property that they are trying to satisfy? What is the question asking for? Then you start by dealing with the most important piece of information because this thing here, dot product is zero, like I told, is a guarantee. It's either a zero vector or it is perpendicular. Then vectors, please remember, I don't want to say this so many times, but I need to keep on saying this. Draw the diagram and illustrate a few scenarios. Why? Because locus is an infinite set of points. To go and visualize the set of points, right? So once you can visualize these and satisfy the mathematical property, then maybe you can draw a best fit line to join the set of points together, and then you can use the locus. Then having said this, you're going to see the word locus appearing in many other contexts, right? So it can be exist in the line, right? Just on the angular bisector or perpendicular bisector. It can also be a curve, but that will be in coordinate geometry and can be a circle, such as this question and just now, the 1 meter away from the star. But this depends on the context. I have no time, so my apologies. So my question 7C, I'm going to go through in another video. Thank you. Bye-bye.